Dear students, today we will derive an expression for electric potential due to a point charge. You know what is electric potential? Electric potential at any point in an electric field is defined as the amount of work done in bringing a unit positive charge from infinity to that point without any acceleration. That means electric potential is the work done per unit charge. Here we have considered a positive source charge at O. Let P be a point at a distance r from O, where we want to find electric potential. Here Q0 is a test charge. We have to bring this test charge from infinity to the point P. Suppose the amount of work done is W in bringing the test charge Q0 from infinity to the point P. Then electric potential at P will be work done per unit charge, means W divided by Q0. Then first we have to find what is the amount of work done in bringing the test charge Q0 from infinity to the point P. Then we will divide work done W by Q0. Then we will get electric potential at the point P. Let A be an instantaneous position of the test charge Q0 during its motion from infinity to the point P. Let X be the distance of the point A from O. The electrostatic force experienced by the test charge Q0 at A, F is equal to 1 by 4 pi epsilon 0 Q0 divided by distance square, that is x square. What is the direction of this force? Test charge is always positive. Source charge we have taken positive. So the force is repulsive. So the direction of the force acting upon Q0 is towards right. That is along OA. To displace the charge Q0 from A to B, what is the amount of work done? The amount of work done in displacing the charge Q0 from A to B, dW that equal to F vector dot dx vector. You see force and displacement, they are oppositely directed, so the angle between them is 180 degree. That is F dx cos 180 degree. That equal to minus F dx. In place of F, you can write this. That is minus 1 by 4 pi epsilon 0 Q0 by x square ds. It is your equation number 2. Now we will find the total amount of work done in bringing the charge Q0 from infinity to the point P. Total amount of work done in bringing the charge Q0 from infinity to P will get by taking integration of dw, that equal to dw integration, that is 0 to w. dw is this, that is minus 1 by 4 pi epsilon 0 q0 by x square dx. You see, is the integration over x. What is x? X is the distance of q0 from O. Initially, the q0 charge is at infinity, so the distance will be infinity. Finally, the q0 is at P. The final position of the charge q0 is P. So the distance from O will be R. So limit is from infinity to R. This equal to minus q0 by 4 pi epsilon 0 x to the power minus 2 dx. Limit is from infinity to R. So this equal to minus q0 by 4 pi epsilon 0 x to the power minus 2 plus 1 by minus 2 plus 1 is infinity to R. So this equal to minus q0 by 4 pi epsilon 0. It is x to the power minus 1 divided by minus 1. Limit is from infinity to R. So here you see, it is negative sign, it becomes positive. q0 by 4 pi epsilon 0 x to the power minus 1, that is 1 by x, infinity to R, that is q0 by 4 pi epsilon 0 1 by R minus 1 by infinity. 1 by infinity is your 0. So this is equal to q0 by 4 pi epsilon 0 R. In the LHS we have W. It is your equation number 3. So now, what is electric potential at P? Therefore, electric potential at P, V is equal to W by Q0, that is Q0 by 4 pi epsilon 0 R by Q0, that is 1 by 4 pi epsilon 0 Q by R. So you got the final expression of electric potential at any point due to point charge, that is 1 by 4 pi epsilon 0 Q by R, where R is the distance of the point from the source charge Q. You remember, electric potential is a scalar quantity because it is work done per unit charge. It is your equation number 4. Here this expression is for air medium or vacuum. In any other medium, V is equal to 1 by 4 pi epsilon 0 epsilon R Q by R, where epsilon R is the relative permittivity of the given medium, or you can write 1 by 4 pi epsilon 0 capital K Q by R. Capital K is the dielectric constant. It is your equation number 5. You remember, as electric potential is scalar quantity, the electric potential, the sign of the electric potential is important. For positive point charge, you note you write for positive charge, electric potential is positive. For negative charge, electric potential, the sign of the electric potential is negative. Now come to the graph. electric potential versus R. V you got 1 by 4 pi epsilon 0 Q by R. That means V inversely proportional to R. So for positive charge, electric potential is positive, you take it is R, it is V, the graph will be like this. And for it is for positive charge, Q more than 0. For negative charge, electric potential will be negative, so the graph will be in the fourth quadrant. It is your electric potential, it is your distance. The graph will be like this. It is for negative charge. Negative charge means Q less than 0. Now we will compare the graph of electric field versus distance and electric potential versus distance. Graph of E and V versus R. You know electric potential 1 by 4 pi epsilon 0 Q by R square, that is E inversely proportional to R square, V 1 by 4 pi epsilon 0 Q by R, that is V inversely proportional to R. As here E inversely proportional to R square, here the slope of the electric field versus R will be more than the slope of the graph V versus R. The graph will be along x-axis you take R, along y-axis you take electric field and potential. It is for potential V. And for electric field, the graph will be like this. It is for E and it is for V. And this point is your 1. When R is more than 1, then electric field will be less, electric potential will be more. When R is more than 1, electric field is less in magnitude than electric potential. When R is less than 1, electric field is in greater magnitude than that of electric potential. You remember this graph. Here we have completed electric potential due to point charge. In the next class, we will study electric potential due to electric dipole.